Okay, section 6.1 is about inverse circular functions, which we call arc functions. Arc, and then whatever trig function. So arc sine, arc cosine, arc tangent, arc cotangent, arc secant, arc cosecant, all arc functions. Write them as trig to the -1, whatever that trig is. So, for example, sine -1. So we can write them with the word arc, but when we read them, we always say arc and then whatever the trig function is. So before we jump into those, we have to review some algebra stuff so that we can make these arc functions happen. So I hope you remember back in Algebra 2 you learned about inverse functions where the x becomes the y and the y becomes the x. On a function, we could draw these vertical lines. These vertical lines only touch my blue graph once, so we know the blue graph is a function. You can draw these red horizontal lines that are in the picture, and these tell me whether the function is 1-to-1 or many-to-1. This x cubed function that I'm drawing on, each red line that I drew touches the function once, so this function is 1-to-1. So let's read over what's on the page and just kind of put it into context. So for a function f of every element x in the domain corresponds to one and only one element in the range. So every one of you, my little x's, has to go to some y or some classroom. Some of you might go to the same classroom, that's okay, but you have to go somewhere. So that means that, and I'm reading right from point number 1, if point A, B lies in the graph, then there is no other point where A is the first or the x coordinate. You can't go to 2 classrooms at once. So if your first period, you my little x, if it says that my little x first goes to Coach Reeves' room, which is 2413, and that's first period, you can't also at the same period go to my room, which is 2412. You can only go to one classroom at a time. So if, in fact, not only every x goes to one classroom, but every classroom only gets one student, then it's 1-to-1. So if this student goes to 2413, and then this student goes to 2412, we have to have way less students in the building in general, but if every student is the only thing that goes to that room, then the function is called 1-to-1, which was my x cubed function up here. It means right here, each element is only used once in the range. If you look down here at my x squared, though, when I draw those horizontal lines, this is what's called many-to-1 because I touch the graph many times. X equals 2 is 4, but x equals -2 is also 4. So that 4 in the range got used twice. So now let's talk about inverse functions for a second. Inverse functions. What this says, I'm going to read this mathematically. It says f inverse equals yx such that, this bar right here means such that, xy belongs to f of x. So what they said was, here's my function f. It has some ordered pair xy. Then when I go to f inverse, I get the point yx. The x and y switch spots. And so you might be sitting there and saying, okay, I remember most of this, all that's great. What does that have to do with trig? Well, let me get there. So here's the problem. When a function is many-to-1, its inverse is not a function. So for example, let me go back to I'm going to draw the parabola from the previous page. So here's my parabola. We agreed it was many-to-1. So if I call this y equals x squared, when I go to draw its inverse, y inverse equals, actually, okay, I'm going to technically write the inverse function. Plus or minus the square root of x. Hang on. Let me redraw this so it's actually accurate. Okay, there's x squared. The inverse has the plus and minus, so it does this. And on the inverse, if I draw these vertical lines, the inverse is not a function. So let's write that. Let's write down what we just talked about. So if f is many to 1, nope, not many to 1, yeah, yes, many to 1, then f inverse is not a function. So x squared is a function, but its inverse is not a function because x squared was many to 1. So if you look at an original functions graph, the vertical line test tells you whether I'm a function or not. So if I have some graph, if I do vertical lines on this, I'm great, I'm a function. But if I draw horizontal lines, we see how I'm many to 1. That means my inverse is not a function. I need to be 1 to 1 to be an inverse that is a function. Okay, so let's go back to the notes. Before we get too deep in this, remember that we read this piece right here with the -1, f inverse, not f to the -1. When we do a negative on an exponent, that's where we do flipping it to the bottom. But that negative on an exponent, like, like x to the -3. Only when it's an exponent on a letter or a number can we do this. This is not that. That is red f inverse. Okay, so let's go through the steps of summarizing the inverse. So first of all, in a 1-to-1 function, each x corresponds to only one y, which means that each y will correspond to only one x. If the function I have is 1-to-1, then my inverse is also a function, which is something we're going to need. The domain and the range flip places. So the domain of the original becomes the range of the inverse, and the range of the original becomes the domain of the inverse. This is a key one right here. The graphs, if you remember, they're reflections across the line y equals x, and there's an example right here. And then to find an inverse, remember we used to switch x and y and then resolve for y. So then down below it says, you look at number 2 on the list. This is kind of a key element where we get problems into trig land. So if we go down here to our trig stuff, I'm going to zoom in. You should be able to clearly see on this sine graph that if I were to go in here and draw vertical lines, I'm good. I'm a function. That's great. But where I'm not so great is when I go to draw these horizontal lines. I am definitely a many to 1 function. But the cool thing about sine, and in fact all of our trig functions, is they repeat over and over again. So if I just take one piece of the trig function and restrict it so that my original function is 1-to-1, then I stand a chance of being able to make this inverse be a function. So let me zoom in right here. We're going to restrict from right here to right here. So we're restricting the graph from -pi/2 to pi/2 because that's where sine is its lowest at -1 and its highest at 1. And no, I'm not looking for a full period. I'm just looking to touch all my values. So here's my lowest point right here. Lowest point, travel up the graph to my highest point. So I've traveled from low to high and touched all the numbers in between. So now on this green piece, if I draw, just on the green piece, if I draw horizontal lines, I now have something that's a function, or its inverse is a function. So now I've made this graph 1-to-1, so its inverse is going to be a function. So we're going to restrict all of our trig functions. I like to call it hot lava, and I'll show you why. We're going to restrict all of our trig functions to just a little piece so that we get the top to the bottom or the bottom to the top, but we don't need that repeat piece in between. So with sine and arcsine, we're restricting from -pi/2 to pi/2, and thus -1 to 1. So on the next page, which is page, I think it's page 4 in your notes, you can see that we've restricted it, and then this is the inverse right here. We've taken all the ordered pairs x, y on our sine graph, and to go to arcsine, we've flipped them all and made them y comma x. So now here is my reflected graph. And you can see that it is a function. It passes the vertical line test. So we are good to go. So here's my restrictions. So we're going to go down here. Okay, so I'm going to write a statement that I hope helps you think of something. So normally when we do a trig function, trig, any trig function of some theta or some angle. And then the answer that we would get out would be the outside of the unit circle would be the ordered pair. Or a point. But when we do arc trig, it's of a point or the ordered pair. And the answer we're looking for is the angle or the theta where that happens on the circle. So on this first one, I just don't like the word arc. I don't know why I never have. So I'm going to write y equals sine to the -1 of 1/2. So this question is asking me, where does sine equal a half? So the first thing you have to do is deal with the hot lava. Always hot lava first. Sine goes from -pi/2 to pi/2. So its hot lava is over here on the left. Do not touch the hot lava. You will burn and die. Do not touch it. It is bad. So where does sine, the y value, equal a half? Well, it's not in this quadrant because sine in the fourth quadrant is negative. So it's in this quadrant. And sine equals a half at pi/6. This question doesn't specify radians or degrees, so I'm just going to go with radians for now. But we've answered the question, where does sine equal a half? Sine equals a half at pi/6. So let's try the next one. Arc sine of -1. Okay, again, this is like a perfect example to illustrate the idea of hot lava. So the hot lava, I'm even going to draw it red this time. The hot lava for sine is on the left. Because remember, I can only go from -pi/2 up this way like this to pi/2. Where does sine equal -1? Well, it equals -1 right here. But I know someone wants to tell me, oh, it's 3pi/2. No. Because if you go this way to get 3pi, you're burning and dying. No, you cannot go in the hot lava. So instead of going the green direction, go the blue direction. Same place on the circle, just with a different name, -pi/2. The last one, again, start with your hot lava. For sine, it's always on the left. Where does sine equal -2? It doesn't. Sine never equals -2 because remember it was bound between -1 and 1. So this one does not exist. So now we're going to move on to cosine and kind of lather, rinse, repeat. General idea is that we have to restrict cosine because its original function is not 1-to-1. And so we restrict cosine a little bit differently. Same values, or very close values. We start up here at the top, and here's the bottom piece. So here's that 1 and that -1 I was looking for, but to make this piece happen right here, I go from 0 to pi. So cosine's restriction is from 0 to pi, and then the output is still this is the domain restriction on the original. So cosine will restrict its original domain from 0 to pi, which means the range was -1 to 1. So when I go over here to arc cosine, which I've now reflected over the line y equals x and switched all those ordered pairs, the domain restriction is -1 to 1, and the range thing that comes out can only be from 0 to pi. Same idea here, same thought process. Remember that arc of an ordered pair means I'm looking for an angle answer. Okay, so let me read this first one. This is y equals cosine -1, arc cosine of 1. This is just a personal preference of rewriting it. I just don't like looking at that word arc. Just not how I learned it. So again, start with your hot lava. Cosine's hot lava was from 0 to pi, so I can't be down here. Hot lava is down here. Where does cosine equal positive 1? Equals a positive 1 right there, so the answer to this one is 0. Do it again. Always start with the hot lava. Hot lava is down here. Cosine is... We're going to cross off the first quadrant because it's negative, and if I want to be negative, I need to be in the second quadrant from cosine. Cosine equals that root 2 over 2 thing at the pi over 4s. The pi over 4 in the second quadrant is called 3 pi over 4. There's your answer. Not super difficult as long as you know your circle and where your hot lava or your restrictions are. Tangent, we also have to restrict. Its restriction is the same as sines. In fact, all of the trig functions get restricted, and let me just draw you a little picture to summarize. So I'm going to draw at the bottom of this page. So to summarize all your hot lava, so this is cosine, secant, and cotangent. They all have the bottom hot lava. They have that restriction of 0 to pi. And then sine, cosecant, and tangent all have the left side. They have that restriction of negative pi over 2 to pi over 2. A picture that's right there. So on page 7 in your notes is all of this summarized restrictions. You can remember how to memorize this blue table. Either way works. So let's do a couple examples. So first of all, note the directions. It definitely says degrees. So this first problem says I need to find arctangent of 1. So again, I'm still going to start with my hot lava. It's tangent. The hot lava is on the left. Where does tangent equal 1? Well, not the fourth quadrant because it would be negative. Tangent equals 1 in the first quadrant. And the answer to that is at that pi over 4. So that is my answer to the first problem. The next one I want to rewrite is this. Secant is the reciprocal of cosine. And if I reciprocate the trig function, I have to reciprocate the number as well. So what I wrote in blue is the same thing that is typed in black in the notes. Our hot lava is on the bottom. I want to be positive, so I want to be in the first quadrant. The x value is a half up there, and that up there place is pi over 3. I have broken all the rules. I just realized, sorry, I need to go back. It says in degrees. So the first one should be 45 degrees, and the second one should be 60 degrees. The next one say we can actually use a calculator, so let's use a calculator. There's a small trick to this, so let me help you with that. So in radians, so make sure your calculator's in radians. We don't have an arc cosecant button on our calculator, so we're going to do that same trick I did in blue right above. This is the same thing as saying y equals arc sine of 1/3, which you can type in your calculator. And then when you type that in your calculator, you make sure you're in radians. It should spit an answer of 0.33983699095. The next one's in degrees. Again, we don't have an arc cotangent. We have an arc tangent button, so we're going to do this. If I call this arc tangent instead, then I have to do, I'm going to put the negative on top so I don't lose it. -1 over 0.3541 to reciprocate the number as well. And when you do that, theta equals, down here, theta should equal -70.500945556. Again, beware of your red box down here that when you're entering negatives and you're in the right quadrant, okay, last couple of problems. These problems are a little bit more conceptual, so we're going to work through these step by step. So I'm going to try to color code. So I'm going to start here on the inside in green. That inside green piece has hot lava, so I'm going to take care of it. It's tangent, so it's hot lava's on the left. And then since it's positive, I want to draw a triangle in the first quadrant. So I'm going to draw a triangle. I need to revise or clarify something. When you see the arc, it means make an angle. In all the previous problems, we have named the angle, pi over 3, 60, 45 degrees, 120, whatever it is, we have named the actual angle itself. In this problem, I'm never going to actually name what that angle is. I'm just going to make the angle. The angle is called theta, and it's right there. We know that tangent is the y over the x, so I'm going to label this 3 and 2. And to find this r up here, I'm going to do 3 squared plus 2 squared, which is going to get me the square root of 13. So r is the square root of 13. We're done with the inside piece. I need to do sine of theta. Theta's right there. Sine of theta equals the y over the r. The y is 3. The r is root 13. You have to rationalize. You can't leave it like that. So your final answer for this problem would be 3 root 13 over 13. Let's try again. Start with the inside piece, which has hot lava. Cosine's hot lava is on the bottom. There's a negative, so I don't want to draw my triangle in the first quadrant. I want to draw the triangle in the second quadrant. Cosine is the x over the r. This is 13 and negative 5. And there's my theta. I don't have to name the angle. I just made theta exist. To find that y piece, you can do 13 squared minus negative 5 with parentheses squared equals y squared. Or you can know that it's a 5, 12, 13 triangle. Now I'm going to do tangent of my theta. Tangent of my theta. Tangent of that triangle is negative 12 over 5. You can put the negative in the bottom if you want. I always tend to put it in the top of my fraction. So there is that problem. Next one's a little bit more than that. So let me just own that first. I'm going to zoom out because I'm probably going to need some more space. The next problem says cosine of something plus something. And that something plus something is a sum and difference formula. So I'm going to call this A. I'm going to call this B. So this is really a hiding cosine A, cosine B, minus sine A, sine B. I'm so sorry. I know you thought sum and difference were gone. They're not. They're not going anywhere. Not for now. Not until we finish the semester. Okay, so I'm going to rewrite this, but instead of A's and B's, I'm going to put my tangent, my arc tangent root 3 and my arc sine of 1/3. Okay, so let's go ahead and do this. So I have cosine of A, which was arctan of root 3. Cosine of B, which was arcsine of 1/3, minus sine of A, arctan of root 3, sine of B, which was arcsine of 1/3. Okay, I prefer to deal with things I know first. This is something I know. This is something I know. Tangent or arctan of root 3. Hot lava is on the left, so I have to be in the first quadrant. And this thing, this root 3, happens at pi over 3s. So this is really a pi over 3. This is really a pi over 3. So let me write what I have. I really have cosine of pi over 3 minus sine of pi over 3. So there's pieces of it. And I'm going to skip to the very last piece because let's keep taking care of the easy stuff. Sine and arcsine are inverses and they undo each other. So those undo each other, which takes this piece down here just to a third. So it was really horrible, but now it's not bad at all. All we have left is this thing right here. Let's deal with this thing. So I have to start on the inside first. And sine's hot lava is on the left. I have a triangle. It's going to be 1 for the y, 3 for the r. So when you Pythag, you should square root of 8, which is 2 root 2. What I just did was I did 3 squared minus 1 squared equals square root of 8 for my x, and then square rooted that, which is 2 root 2. Okay, so let's keep going. I still have a cosine to do. Cosine of this triangle right here is the x, 2 root 2 over the r, root 3. Okay, let's conquer this. So cosine of pi over 3 is 1/2. The next green piece stays 2 root 2 over 3 minus sine of pi over 3 is root 3 over 2 times that red 1/3. And then we're just going to multiply our fractions together. Straight across, 1 times 2 root 2 is 2 root 2 over 6 minus root 3 over 6. Since those denominators are the same, I can write this one last time as 2 root 2, that doesn't look good. Let me try again. 2 root 2 minus root 3 all over 6. So a little bit of a doozy of a problem, but you can absolutely manage that, I promise. Okay, one more page. We can do this. Okay, so no different. Start on the inside and notice the 2. So this whole thing is really a tangent of 2 theta, where this thing right here is my theta. So that's a double angle formula. So that formula is 2 tan theta over 1 minus tan squared theta. So we got to deal with this theta thing first. Let's do this. So sine's hot lava is on the left. It's positive, so I draw a triangle in the first quadrant. This is 2 and 5. 25 minus 4 is going to make my x squared. Square root of 21. Then you have to do tangent of this theta. So let's do that. So I get 2. Tangent of that triangle is 2 over square root of 21 over 1 minus 2 over root 21 squared. So this is going to equal 4 root 21 over, when you square this, you're going to get 4 over 21. So I'm going to call my 1 21 over 21. So when I subtract them, I get 17 over 21. I'm going to rationalize the top. So I'm going to get 4 root 21 over 21 over 17 over 21. I'm going to keep change flip. The 21s will cancel off, which means my final answer is 4 root 21 over 17. Okay. Not horrible. Manageable. And yes, your double angle formula, it's still hanging out. It didn't go away. On the next one, tangent of u, or arctangent. Tangent's hot lava is on the left. The u is positive, and that u is like a u over 1. So the u is your y, and the 1 is your x. So u is the y, x is 1, u squared plus 1 squared is 1 equals my r squared. So this is the square root of u squared plus 1. I've made my angle, my red angle theta, exist. So sine of theta equals the y over the r, which is u over square root of u squared plus 1. We have to rationalize. We cannot leave it like that. So you multiply top and bottom by u squared plus 1 over square root of u squared plus 1. Your final answer will be the u that you had out front times square root of u squared plus 1 all over u squared plus 1. I know, a very long video, and I'm apologizing because it's a longer section. Last problem, though. This is, again, cosine of 2 theta, where this piece is my theta. And I'm going to use a little trick, but we'll take care of that. So, whoops, let me do this in a color. So, let me do this right here in green. Science hot lava is on the left. It's positive, so in the first quadrant. I don't know what happened to my axis, sorry. This u is a u over 1, which is my y over my r. You can find that missing piece if you need to, but we don't need to because cosine 2 theta has 3 versions of the formula, and let's just use the one that has sine in it. 1 minus 2 sine squared theta. This is my theta, so we can do this. 1 minus 2, sine of that triangle is u over 1 squared. So I really have 1 minus 2u squared. And that is my answer. What a great problem to end with.